Hello, class. Uncle George, all the boys and gals in the class. Hope everyone's well and is doing well in Chicago. This is Tony from California, and I'm going to talk to you today about accelerators, namely GPU computing. And all my stuff is public, Bitbucket, as well as my YouTube videos, screencasts. So I made one before for like half an hour if you want the first primer. But really what we're going to talk about is it worth all the trouble of using this kind of expensive hardware to speed things up? And we're going to just try to prove that, it really is kind of helpful and speeds things up. And we're going to do a number of tests across different platforms. So this is really interesting stuff because we're going to cross over to C, CUDA C, Java, MCode, OpenACC, closed source and open source type things. So it's a fun challenge because, as you're going to see, when we're testing at home, we have different hardware, and then we go to run on the server, there's different hardware there. So we have to change our code if we want it to work. So it's kind of something you got to wrestle with as you kind of encounter new hardware. And I'll show you specifics shortly. But again, we're talking about GPU computing, and that means that video card inside your laptop, it doesn't just render pretty graphics magically. It uses a lot of math functions to scale byte calculation, sprite graphics into vectors. A vector is just like a column in Excel, and then it uses some vector math like matrix multiplication to actually render a lot of images on your screen. So about 12 years ago, folks started saying, well, if it can do that, why don't we just use it for math? It's using math anyway behind the scenes. So that's how we got into these video cards, GPUs, in other words, to accelerate our processes. Okay, so NVIDIA makes the most popular ones, and then AMD makes popular ones too. Okay, but the most extensive libraries that are out there that we can kind of piggyback off of are called CUDA, and they're made by NVIDIA. So it's their monopoly. They make you use their cards if you want to use CUDA. If we want to use open source means we can use any device. Then we have to use things like OpenACC and OpenMP, and the libraries aren't quite as powerful, but they're still pretty good. So we'll look at all those things. And finally, the big new thing for today is Java. Java is a great language. I've gotten used to it. And the question is, how the hell do we use these accelerators inside Java? Because again, NVIDIA uses CUDA C, C++. So can we still use this great language of Java and actually work on these GPUs and do what we call hybrid computing? Okay, all hybrid computing means is we're going to split up some of the work on your CPU, your Intel i7, if you will, and the GPU. And when both these things are sharing the work, you get faster results. Okay, so we're going to show that in Java, if we use wrappers is a fancy word for making functions or using libraries to somehow incorporate these CUDA C functions, that we can still use Java and it still runs pretty fast. Okay, wrapper isn't quite native; it's kind of one level removed. So we just want to see, finally at the end, is this another possible way we can do GPU computing? And we're going to see that we can do it. It's definitely a little tricky though. So, just getting your environment set up for this stuff really is half the battle. It can be a real pain in the ass. But once you kind of practice, get the hang of it, it's fun. So let's just go to the baseline problem. The problem is we're gonna build a simple model of the world. It's gonna make a prediction. Think of a model as a regression equation. Y equals mx plus b. X is a factor, m is a parameter. M is a parameter like beta. And as you roll through time, you have to update that parameter to make it fit the world, right? Now, since I'm a boring finance guy, we're kind of useless, but our problems are big because we have these huge data sets and we're doing a lot of optimization, portfolio optimization. It's kind of a nice problem to try out this GPU computing on. Okay, so we're going to start with a simple model and do it in C#, C, CPU only, see how fast this stuff runs, and then finally try it on all these GPU type programs and see if we can speed it up. and we're going to see at the end that we can. But it's definitely a lot of work. Okay, so about a year ago I started doing simple examples just on my local hardware, and a lot of time this stuff would not work on Tesla servers or foreign remote servers. Half the battle is kind of changing your code to get that to work, and of course all the Java stuff and the MATLAB wrapper stuff is new. So again, folks, in the finance world, because our bosses tend to be older gentlemen, we are stuck in C, C++ a lot of the time. It's not to say it's a great language, it's just the way it is. Also, secondly, packages like R and MATLAB stats packages are very, very popular. Okay, and we're going to show you how we do GPU computing inside MATLAB and things like Mathematica. So let's get going, and let's just look at this simple model here. Okay, now this is C#. We have a nice GUI, right, that I made, pretty nice. Got a chart here, got a z-score. Z-score just tell us, is a stock trading high or low? Is it rich? Is it cheap? It's like going clothes shopping. Do you want to buy a suit when it's marked up? Will you still buy it because you want it, or do you wait till it comes down on sale? Do you wait till the price falls and it's cheap? So in trader lingo, rich cheap means dear or near, or expensive or inexpensive. Okay, so we want to find some statistical measure. This factor we'll call z-score. That's your y equals mx plus p. That's your x. Z-score is your x. And then we'll have to update the parameters, your y, if you will. Now, Kurt Gödel was a famous Austro-Hungarian after World War I. Einstein looked up to Kurt Gödel so much. They were both at the Advanced Institute in Princeton together, that Einstein, in a way, it's not widely known, but he kind of worshipped Gödel. And the thing that Gödel kind of came up with was this thing called the incompleteness theorem. So I just have to give you guys a little bit of a primer in finance, because it'll explain the model a little bit. And what he said was that it's okay for things to be incomplete or imperfect. In fact, there's always going to be some kind of contradiction or some imperfection, no matter how hard you try. Okay, so he kind of gets into like this fuzzy logic, fuzzy sets. He lays the groundwork for fuzzy logic. And when modelers like me come along, and again, we're not building rocket ships, we're just trying to find patterns in finance, seeing if it can make us some money, and if it can't, we keep trying, It's kind of like that movie, There Will Be Blood. You're really fighting to try and find oil, or in finance, we're trying to find a pattern or factor. And if we can find something that'll hold up for a while, we might be able to make some money. But just be warned, it's very hard. It's addictive, but you can kind of go a little nutty just constantly searching. But that's what people do in this business, and we just call it finding alpha or excess returns. So anyway, back to Kurt Gödel. He basically says, okay, relax that model, that regression, y equals mx plus b. Relax it and just say, put it into kind of pseudo language and kind of like Boolean logic, just a lot like computer code. So we can also specify the model and just say, if this condition true, then buy or sell, then X or Y, yeah? So that's what this model ends up being, but you can think of it as a regression as well. Of course, a regression is still linear. If we want something super nonlinear, we switch to neural nets. That would now be like y equals mx times mx2 times mx3. There's no plus signs on the right-hand side of that equation. It's all multiplication signs. That would be highly probably overfitted and nonlinear. Here we're not going to do that. We're going to stay with this one factor model. We just have one trigger, one factor telling us when to buy or sell. Okay, so here's Facebook, right? It's going to go to Yahoo, pull down the data for free. Now these are predictions. We're not front-running or doing high-frequency trading. That's legal for now, though the law will change. We're actually trying to make predictions and hold positions for days, right? So this is the hardest thing in the game you can do, is to try to see into the future. It's very hard. We're not reacting, we're actually predicting. So it's a big difference in this type of model. So our back test, we want to see how well we would have done. You can see results down here, okay, and key stats here. But we can see this is the C# model. It's a one factor. This would be our baseline. We can see how long it takes to run. We could put in, of course, the more data, the longer something would take, right? So We see these parameters here. We see like a moving average. Moving average says take the last 20 days of prices and average them. That's a parameter. That's kind of like that y equals mx plus b, m, or beta. It's another parameter. And of course, once we hit optimize, it's going to try every combination of parameters. So that's that combination math, right? Two parameters with two choices each would be 2 squared. Okay, no big deal. But in the real world, we have 4 or 5 factors in a model. We can often have hundreds of models running simultaneously. So that's when this kind of portfolio optimization really runs into the wall. That's where we need these GPUs to speed things up. Okay, so we can get just millions and millions of combinations, and if we're kind of fitting intraday, refitting these models, we can see that we're going to run out of time. And in older days, we actually would have to wait days for our results before we could change our model. And just to say something about finance, this is an unnatural, man-made world. Okay, it's not like physics, where a lot of things in the physical world are very normally distributed. In fact, when they look for key results in physics, they have a cutoff of something we call 5 sigmas. If any event is beyond 5 standard deviations, it's 99.999% certain that it's not random. Physics guys, like at CERN, for example, looking for Higgs boson, they'll say, you know what, okay, we found it because it's over 5 sigmas. But in the finance world, it's so crazy and behavioral, because again, it's a human world, it's an emotional world. We have 20 sigma events, 17 sigma events, 9 sigma events, 5 sigma events every year. Every couple months we got one happening. So it's a very bizarre world, okay, because it's an unnatural world. So that means when we're using our models and our stats, we really have to take them with a grain of salt and maybe try to use non-parametric type approaches, right? But that's a whole other discussion. Just keep in mind, it's kind of a crazy world. You're digging for gold, but very often you don't find anything, or it's fleeting, and you have to find new models. Okay, but when we see this model and we need to run this optimization, okay, so this is a CPU only model in C#. Okay, only using the CPU, and you can see it took some time, to get the results for IBM. Okay. I also made this model in C. C, you can't really make GUIs the same way as in C#, .NET C#. The old C, you had to it's for straight through processing and math, okay, and that's really what I'm most used to. But in C, same kind of thing, CPU only. We're going to see how long it takes to run these models and use that as a baseline and try to prove to ourselves as we get into the GPU that we can beat these times, okay? So, all right, let's get out of C# now, okay? And I'm in Windows right now because it's just easier to run all my other applications like MATLAB. But keep in mind, when we work on the server, we're going to be in Linux, okay? A lot of the scientific computing is in Linux, so kind of need to get used to it. Now, let's talk about something, let's talk about the little device in my desktop. Okay, these cards can be expensive, $1,000, $2,000 to $4,000 for the professional Tesla servers. That's expensive. So most people are going to have one card, just like me. And you can see here the description of my card. Okay, and this is why it's hard working on other other hardware. That means the school server. See the school server over here? See, I'm logged into VPN. I'm using Bitwise Tunneler. Look, school's using a different driver version, and it's got different memory, different amount of GPUs, clusters, if you will. We call them cores. Different speed. Integrated GPU sharing host. No. Support page lock memory mapping. Yes. Device has error correction for its memory. We call it VRAM or video RAM. Enabled. See how different this is from my own device. This is why last year, from an independent study, a lot of my code did not work on the server because I was not adjusting it to work on the server. So you see we have different memory limits and stuff. So this stuff comes into play in your code. You must be mindful to update your code and really study the device that you want your code to work on. Okay? So look at this. Max texture dimension size. 2048, 2048, 2048. Okay, okay, it sounds nerdy, but this stuff will blow your code up. It will not work, okay? It will not work if you do not adjust your code, okay? You kind of have to learn that the hard way. Again, a lot of this really is playing around. See, look at this. Max dimensions of a block, 1024, 1024, 64. Okay, in that case, it does match the school's Tesla server. Okay, so that's fine. But there are some differences. Like this does not have error correction, and when you're promoting or casting, especially when you're playing around with float, there's double and float. You know, think about 16 decimal places or 8. GPUs work really fast on single precision, so sometimes we try to be really clever and have values be float, and then when we need a double or more precision, we cast them to float, or they can get promoted automatically if we're not careful, and that can slow down your program. But don't want to go into that too much. But we're often switching between float and double. Okay, so error correction on the server checks more robustly all the results for float, and if it can't be sure of it, it'll return a 0 sometimes. So just be mindful that these devices are different, and that's part of the challenge of working on different hardware, and it's kind of why the GPU computing is really interesting and challenging. Okay, so let's get out of that now, and we can basically see that in my earlier video about a month ago, I showed you that all the stuff on my own machine works. Okay, so I don't want to go through it again, and I think I also ran it on Tesla, but we can go back there, run it again just to show that everything's good. And folks, all my stuff is out on Tesla, all the various demo, that's ACC, multi-GPU, CU, Java model, okay. And also my my Bitbucket is public, right? And this is where I put my midterm. This is it right here, right? This is that markdown format that George had asked for. I didn't know how to get pictures in here, but anyway, you see the to-dos. That's the stuff that I really had to do last month or so. That's the really brand new stuff, okay, like the Java, trying to get GPU working in Java. Okay, so we can just go through here, and also downloads. There's a bunch of stuff in downloads, okay, so everyone feel free to do whatever they want here, okay. But basically, let's just go to the server here. Yeah, I'm just going to run real quick one market. Again, look at the earlier video. I'll put a link to it in Trello. But yeah, if I go here, I can just kind of go here. Debug. Okay. I could just kind of go here, CD. Just go here. Be lazy here. Trying to speed up, folks. But this is kind of a deep subject. You could really spend hours. You could spend hours doing this, but you can see it's already compiled. We could compile it again. It's not really gonna make much difference, but we get a lot of warnings because some of my syntax, on different versions of C or CUDA, sometimes it's outdated. It doesn't like the way I'm using something, but it's alright. It's just warnings, and obviously we can run it there just doing that /. Okay, so I'm just doing one market now. In reality, we've got 30 markets with 30, 40 years of data. Yeah, so yeah, we can see it ran, and it's going to stick output. Here's all the raw data. Here's all the output. See, in sample, out of sample. Here's the thing to remember about the whole parallel processing, right? This is extreme level of parallel processing we're exploring today, right? What we're doing is we have a bunch of markets with a bunch of parameters that need to be optimized, right? Exhaustive optimization means we try every combination of parameter, okay? What we can do is just say, look, I got 4 GPUs, right? Remember up here, folks, we just did that device thing? Well, anyway, if you remember before, we had 4 GPUs on the Tesla server at Loyola, right? So I can run like 6 markets on each server and then have it send the results back to the CPU. So again, there's all this exchange between the CPU and the GPU, okay? And that's the tricky thing, you know. You have to watch out for shared memory, and you have to time things and synchronize them sometimes, you know. So if you look at a simple function, doesn't look that simple here, but I put all my functions on the bottom. Okay, this is a GPU function. This is a CUDA-C function, right? You got this underscore global, right? We call these CUDA kernels. You can see they never return anything explicitly, hence void. What they do is the results get stored on the GPU, and once they're done, I have to explicitly push them back to the CPU, you know. So remember, we're going to do some calculations on the CPU and then do the really hard stuff or big stuff on the GPU. You see, I added inline comments to all my older code just so it's a little neater. I know there were some complaints about that, but you know, just if you read the paper in the download sections or in my Bitbucket, this will all make a lot more sense. But remember, I said you got to worry about block dimensions and grids, and you don't want to go out of bounds or get a segmentation violation. Basically means you screwed up something on the memory. Okay, right? Threads, blocks. Okay. You know, you just got to be mindful of all this stuff, okay? So this is CUDA-C. It's an extension of C. We're going to use NVIDIA's compiler. NVIDIA's compiler, in turn, still needs a C compiler, okay? In Linux, that's often GCC. In Windows, that's often a Visual Studio C compiler. Okay, so they all work together. A lot of compilers working together, okay? So you got to kind of be careful and make sure your environment is set up correctly, okay? So I have a primer in C. It's in the paper. People can read that. I don't want to get stuck on that, but just remember C. It's not object-oriented. It's just for straight-through processing, okay? We have this in the preprocessor, including all our headers or libraries up here. We have some kind of hard-coded definitions, yeah, that we do up here. Think of them as macro variables. And we forward declare all the functions we're going to use, and then here's the main. Here's the main entry point. With C, you use pointers. You know, pointers, when you get used to them, are pretty clever. It's kind of a way of vectorizing your code. And you hear that, you don't know what it means. But a vector is a column in Excel. Instead of me timesing one number, each cell by cell, I want to times a column by a column in Excel. You know, pointers help you do that. And that's really what this, it's one trick in GPU computing you got to do. You got to vectorize your code, because you're going to be running much faster when you're doing matrix multiplication, right? You're taking many columns in a matrix and multiplying by, you know, output from another matrix, and this greatly speeds up your code, right? You do not want to go through cell by cell, step by step in your functions, okay? So it's something you kind of need to get used to. Also, this math, these operations have to be independent. That means, you know, I can't rely on I minus 1 because we're breaking up the data and the work. And so, you know, one GPU device, you know, Tesla has 4 of them at school. One GPU device can't call over to the second one and say, hey, bud, can you give me the value for I minus 1? You can't do it, you know, so you got to be very mindful, you know. To get a parallel speed up, right, in your code, you got to make sure operations are independent. And if they're not independent, there's some tricks to maybe make them independent, or you just have to do that part of the code sequentially, okay? So sequential versus parallel, okay? But just keep in mind, you know, this is extreme parallelism, right? Look how many threads I can do, 256. Remember on the CPU when we were working in algorithms class with Java, you maybe, you know, could get maybe, you could put a lot of threads in there, but it was stupid after a while if you only had like 4-core CPU. But don't forget, we've got thousands of cores here, right? So look, 2304. Okay, that's just on one device. So that, that means each one of those could be a thread. Okay, so anyway, that's a quick look at the C code. And if we look at a CUDA kernel, again, we covered this already, but a very simple one, right? Notice extern C. This is for the Java part later on. Extern just says, look, use the C compiler and don't mangle the name. Don't rename this function, because when you try to call it later, it won't work if the name is changed. So when you see extern, that's what that means. Okay, but anyway, here's a CUDA function or kernel. Again, when we call it, again, this is CUDA C. It's an extension of C. You often see this triple chevron here, right? And you got to say how many blocks, threads, shared memory, which stream. Okay. All right. So let's just talk more about extreme parallelism. Okay, because there's some tools out there that can help you look at your code and say, look, man, speed it up. You're not doing good enough. Okay. This is called a profiler. Okay. And let's just talk about parallelism, because we used to talk in algorithms about threads. Okay, but what I'm trying to tell you is there's more to parallelism than threads. There's threads, streams, and there's multiple devices or GPUs. We want to lean on all that power to get the maximum speed up in code. Okay, so you see here, right? All these different streams. What's a stream? Well, look, if I've got 4,000 cores on one GPU, and I only have 2,000 elements in my array or 2,000 stock prices to analyze, well, you know what? I can divide that device into two chunks, or two halves essentially, or two streams, and then do parallelism within the device itself. And each stream would be running multiple threads, right? They could be running maybe 1,000 threads. So stream 1 would be the first half of the GPU, running 1,000 threads a pop. Stream 2 would be the second half, running 1,000 threads a pop. Okay, so we call this multi-streaming, multi-GPUs, and this is taking it to a whole higher level. Okay, so I just wanted to talk about that. This is a nice, you can click on each thing and it'll tell you, hey man, how long did it take? What's going on? All right, this is telling you, hey, multi-processors, how many did you hit? How many threads? And really what we want to get to is something called occupancy, okay? And that's something you just got to think about. Each device has so many cores, and it's a different size. You have to think about, am I using the right amount of threads and blocks, okay? Generally, in GPU computing, threads and blocks need to be a multiple of what we call warps, W-A-R-P. I don't want to confuse the class, but it takes some getting used to. Basically, I will show you right here. Warp size, C32 right here. Things kind of have to be a factor of that, right? So if you look at my code, you can see I probably have blocks of 16. Again, each CPU device is different, right? So everything kind of has to be, all these amounts have to be kind of a factor of each other, divisible. Okay, that'll help speed up your code. Okay, but what we're solving for is something called max occupancy. Okay, we're trying to use as much of the device as we can. We don't want to be running operations and find out that 90% of it didn't get touched. All right, that's kind of a waste of space. All right, so okay, let's leave that alone. Okay, but now let's get away from CUDA C and talk about real quick about open source. Okay, and what we mean by open source is that now I don't need an NVIDIA GPU. I could use an AMD GPU. I could use whatever I want. But the syntax now is different, and these are different libraries, right? In fact, we may have to modify the library ourselves and fix some things for our code to work. And this is where it gets kind of hard, we have to make a lot of these functions. We can't just find them somewhere and use them, okay? The thing about any of these C variants is there's not a lot of libraries out there, so you have to probably build some of your own. Just to get a moving average in math, there's really not a big math library in C, so we have to write the code, So you tend to be forced to really to learn, you know, and kind of get to the nuts and bolts. Okay, um, so this is OpenACC, and we see like the syntax is different. We have this pragma ACC now here, huh? Everything now is a pragma when we start a loop. So there's subtle differences like that, and I could go on and on. But this is an example of open source GPU computing. We are not using CUDA-C here. We are using a different compiler, and we do not need an NVIDIA device. We can use any device we want. Okay, so that hence the word open. Okay, so we see that ran. Okay, and this is also on the Tesla server. But remember, the Tesla server, none of us have admin rights, so you can't just install your own programs or libraries per se on it. You know, we don't have full power. So stuff is on the server, but not everything's going to run, and everyone's open to grabbing this stuff and looking at it if they want. Okay, so that's OpenACC. Now let's also get away from this classic CUDA-C that really I was doing more of like a year ago. Let's look at wrappers. And wrapper is a fancy word for kind of like an interface in C# or Java. We need some kind of translator or functions to make something work in another environment. Okay, and so a wrapper is just like making functions to have stuff work. And now this is a stats package called MATLAB, and it stands for Matrix Laboratory. So right here, the theme of matrices. Remember, I talked about vectorizing your code. It's really built in here, you know. And with a lot less work, I can get a lot of calculations. Now they do have extensive math libraries, so these kind of packages can make you a bit lazy, but they are popular in finance. And we can see that MATLAB sees my drivers and is saying, okay, bud, yeah, I see your GPU, okay? And again, it's telling us the max dimensions. Those are my limits for my calculations, okay? And I just want to show you that the code, I don't want to get too far into it, but again, this is fully working now. Again, a lot of this over the last year, I just keep working on it, trying to improve, which is why I wanted this to be my project. I just wanted to keep working on it. But we're using wrappers now, so this is not native CUDA-C, okay? Behind the scenes, it's communicating with NVIDIA's driver called MVCC, and the C compiler to make this work. But I'm going to show you it's a lot slower. So this is one of the trade-offs here. When we get away from native CUDA-C, okay, stuff runs slow, you know. Look, see my z-scores there, and it keeps going and going and going. This is about 5 or 6 times slower than native, and you know, I'll just pause this, but that's MATLAB, okay. And here's what's really interesting. Now we're going to look at Java, you know, because I fought Java a lot, but now I actually like it a lot. And don't forget that George, our professor, he wrote a high-performance book in Java. So we might be able to help George out by showing George that, you know what, you can use GPU computing in Java. You don't have to go to C or CUDA-C. You know, if we just use these wrappers and maybe modify some libraries, we can get stuff working. And that's kind of nice. You know, and not only that, but it runs pretty damn fast, almost near native. You know, that's the big question mark is, what's the trade-off going to wrappers? Well, it runs slower. How much more slowly? Geez, I don't know until we run it. You know, so let's go look at it. Okay, and this gets a little tricky, so I don't want to go on too long. I know this video is getting long, but again, this is kind of a deep subject. You could really study this for a whole semester. Here we have Java. Okay. We got a math class. These are like z-scores, all that, and we have the main entry point. Okay, and I'm going to use some libraries made by some other guys just to get the NVIDIA drivers to work in Java. Okay, so that's that. Okay, but I still need to make my own functions and CUDA kernels and maybe modify some of those libraries. Okay, so let's just take a step back and see what happens. I just want to show everybody, because we're going to use something called again, I don't want to confuse people, but we're getting kind of extreme stuff here. There's something called a PTX. It's basically like PTX stands for it's kind of like POSIX and C. PTX is a way of getting parallel threads working. Okay, you often can convert stuff to PTX, and then it can work PTX file, and then it can work in other languages. Okay, let's just kind of leave it there. But I'm going to delete this, and I just want to show you what's going to happen. So we're in Eclipse here. We know that's Java. Here's where all my output. Here's my input. Here's my raw market data. Okay. Right, we see that, date, open, high, low, close. You can get a lot of this for free from Yahoo Finance. It's very hard to get this environment to work, so as a shortcut, you should put stuff in the root of your project folder to save yourself some time. Otherwise, you have to modify the class path. Yeah. Build path, configure, and point to all these libraries. So your jar files, your JCUDA homemade libraries, the JCUDA pre-made libraries. Okay, it gets a little complicated. So if you want to save yourself some trouble, put whatever you need right in the root of the directory. Okay, see right here. Okay, and notice what's there. What we have there is the CUDA-C, the original CUDA-C function, and there are many C functions, which now will get done in Java, and there's also this pure one that's going to run on GPU only, and we call that a CUDA kernel or CUDA-C. And here it is. It's going to take in some z-scores and some returns, and then shoot out to the GPU some P&L and positions for each day, and then eventually those are going to get transferred back to the CPU. Remember, this returns nothing explicitly. It just calculations get left on the GPU, and we got to push them back to the CPU and clean out the memory on the CPU and the GPU. Otherwise, we'll get a memory overflow. Okay. Okay, that often happens in C, that you can run out of memory. Okay, you got to be careful. In C, there's no just-in-time compiling or garbage collection. You actually have to manage your memory. So that's the pure CUDA-C function. But look what we're going to do in Java. Okay, we've rewritten all our other CPU functions in Java. Okay, and look what's going to happen here. Okay, you see now how all these functions, they don't quite look like the CUDA-C I showed you earlier, right? Look at this, CUDA, memory, Alex. See, they're all different. We had to work on these. Okay, we had to modify some of these libraries and make new functions ourselves. Okay. Now look what happens here. Remember I said CUDA-C is all about pointers. Okay, Java doesn't have pointers; it has references. So this Java has to kind of retranslate C's pointers, right? The CUDA function's pointers, okay, into references, and then to get them to work in Java. Okay, this is what we mean by a wrapper. Is we are making functions that will somehow translate through the CUDA-C to make it work in Java. Okay. Now this looks familiar. Again, we're specifying threads and blocks, kind of like the CUDA-C. Okay, we have our synchronize. Okay, and now of course we see once the results are done, we're going to go copy device back to host. Host is the CPU. Okay, look what happens here. I'm going to tell Java to suck in the CUDA-C file. Okay, this is pretty cool. See this? That's the raw CUDA-C file. I'm going to tell it to convert it to a PTX file, then load the PTX file, and then run the rest of the Java program. Okay, so you've got a lot of compilers kind of working here. You've got the NVIDIA MVCC compiler, which in turn needs the C compiler, which in turn Java's telling it to translate that to a PTX file, okay, which then gets loaded into Java and gets run on the fly. Okay. See this function, prepare a PTX file. Alright, so this is about as complicated as it gets. I mean, this is pretty hard. I didn't. This works. I don't know if I got the super robust version working where it would work across multiple streams on multiple GPUs, but I basically have a single GPU working and it's pretty damn fast, you know. In fact, we're going to run it. I'm going to show you that it compiles and it creates a PTX file because right now there's nothing there, right? This is running on my desktop, folks. This will not work on the Tesla server because I cannot just load my own homemade programs onto the school server, right? There's a limit to what I can do. I don't have admin rights, but if we look in here, you know, we can see everything's here. And notice there's a different version of drivers on this server versus my own device. So let's just go run this. Okay. Look, it made the PTX file and it's running all this stuff. Okay. And we're going to see how long it runs. We just want to show that even with wrappers, you know, Java is still pretty damn good for GPU computing. It's good. We don't have to leave the Java world and retreat into C. We're okay, you know. Alright, now this is a very large file, the output, but I guess I could open it real quick. But anyway, we've proven that JCUDA works, and it's another nice trick. So we've covered JCUDA wrappers, MATLAB wrappers, open source ACC. We've covered CUDA-C and NVIDIA, and we've covered, you know, just the CPU only stuff in C# and standalone C. So what we prove basically is, you know what, we did pretty well. We did pretty darn well if we look at the results. Well, it's hard to see, but and I haven't updated them all yet. I'll do that later, but we can indeed see that GPU and CPU is faster than CPU. You know, just look at this. You know, this is our starting baseline, if you will. We just keep getting faster and faster, okay? And Java would be, the JCUDA Java stuff would be somewhere in here. Okay, so not quite as fast as native C, but you know what? Very good, very good. Okay. Yeah, here's MATLAB. All right, so anyway, so we're pretty happy with the results. And when I break down my code in my paper, everyone is welcome to look at it. I really spend a lot of detail pointing out, you know, the essential points, a lot of notes here. I added in-line comments because a lot of stuff was sloppier before. Okay, so, you know, if you go through this, it's also a tutorial in C, you could probably self-educate yourself to a large degree, and then when you play around, it might speed up your learning curve. Okay, so for the fanciest, powerful supercomputer now, it's actually at Oak Labs in Tennessee. You know, and you can go and look on their website. Here it is. China just beat us again by a little bit, but you know, you can kind of see that how big. This has tons of GPU cards, NVIDIA stacked together. It's called the Titan, and you know, that's basically going to do it. So we can see kind of, here's Oak Labs. You can see the processing power and teraflops, and you know, in the old days, and we just see what a GPU server looks like, large scale, diverse because the hardware is diverse. You got CPU and GPUs. It tends to be very secure. It's using some kind of message passing. For storage, there's memory on the GPU called VRAM, RAM on the CPU, and some of that can be shared. And the memory can be transferred sequentially or synchronously or asynchronously. And that just means, you know, each CPU doesn't have to wait for the other one. It can just shoot it back when it's done. But you still can't always do that. Sometimes you have to wait and slow things down. Okay, synchronously. Otherwise, you get back garbage results. Okay, so that's basically going to do it. The evolution of Oak Labs. Where is that? There was a good one. I don't know where that picture is, but you see, like, In the old days, you were just using Craze. Yeah, here it is. Just CPU only, and now you see they've gone to the GPU. So everybody's kind of doing it now, and I really encourage folks to get back into it. All right, so that's going to do it. I'll clean up my final paper and put it on Google Docs. And again, the README here is basically the midterm, so it's got most of the stuff you need. No pictures though. And you see all the source code here, and if you want raw data files, well, they're there too. Okay, so that's going to do it. I thank everyone, and everyone have a great semester. All right, thanks very much.